Welcome, everybody. Thanks for joining today. I'll start the presentation here in a second. So my name is Dustin Hillard, and I am CTO at Versive, and we are a machine learning platform company, and we're focusing on a particular product on top of that platform, which is something that detects advanced cyber adversaries using machine learning. And so today I'll talk to you about a little bit of an overview of what that problem looks like and why machine learning is interesting for it, and then how we use machine learning to improve the defenses of networks, and then a bit more detail about machine learning approaches for detecting these cyber adversaries that we're using today and where that might be going next. So first, an overview of what this is. So why is machine learning even important here? What security teams are dealing with today is a massive amount of data coming from different instrumentation they have on their networks and on their endpoints. And so there's a lot of complex data that they have to deal with, and they have to kind of understand what the risks are to their network, and it's very difficult to discover these. You have to look across them, and right now it's an extremely manual process, and really there's no amount of human effort that can accomplish this. And so where the field is going is starting to build these machine learning approaches that can help to automate the initial tasks of this and really consolidate the information so that people with the expertise in the field can act on it. And so there's cybersecurity in general is an extremely broad field and term. And so I want to give you a little bit more detail about the part of the problem that I think is most important today and what I'll be focusing on. And so there's something called the kill chain that a lot of people use to reference the different aspects of cybersecurity, and this is a version of it. We think about it as the kind of adversary lifecycle. So this is what does someone or some organization have to do to be successful in order to achieve their goals, and these are the kind of primary activities that are required. And so the first two are where most of the field has been focused in the past, and that's around what an adversary does from the outside as they work to obtain access to a network. And so that planning and access phase is really understanding, what they might want to go after, and then how they're going to get into a network. And so that's, firewalls and antivirus and malware and all of these approaches to keep out malicious actors and stop malicious access is where a lot of the field has been focused to date. And what we're looking at is then the internal aspect of these behaviors. Internally, these behaviors, reconnaissance is when after there's access from a machine, the reconnaissance phase is looking around the network to understand what's there, what data and services are, and where the target is that they want to compromise and grab that important information from. Collection is then the kind of pulling of that data and staging of it to prepare for eventual exfiltration to take it off of the network. And so importantly, these final three stages are not necessarily something that has to be accomplished with any of the typical things that we hear about in terms of malicious tools and so forth, and even internal employees that have that decided to do something malicious can accomplish this as well. And so these require a behavioral approach for discovering these types of activities, much more so than the traditional conception of how we build a signature to discover malware, or we have a threat feed that says, this IP address or this external domain are bad. This requires a much more behavioral understanding of what's going to happen. And so you can't rely on past information about what's bad. You have to be able to identify that behavior in a network looks different and unacceptable activity on that network. So to give you context on a couple of examples, just talk about kind of two different of these advanced adversary campaigns and what they look like. And so this one was a particular organized crime or activity, which was so over 100 financial institutions were compromised in this way. And so basically emails with exploits were sent to a broad set of people, and some of those were effective. And so at a large number of organizations, someone there was basically human error, right? And clicking on a link in one of these that allowed that machine to be compromised. From that point, that's that, initial access phase. And it's after that that it starts to get interesting, and that most organizations are unable to detect this kind of behavior and understand what's happening beyond that initial exploit. So if you miss that, then you start to be blind to the real business risk that happens after that. And so what typically happened after that was this reconnaissance phase of, they got through on one person's machine, and now they have to look around and understand how they can get to an administrator's machine was the primary target, because from that administrator's machine, then they would be able to understand how that bank operated and have the ability to steal money was the eventual goal here. And so once they did that reconnaissance and found their way over to an administrator's machine, then they were able to basically do a screen capture and watch what happened. And so they were sending all this information out right as they were doing this reconnaissance and understanding. And then eventually, once they kind of learned the systems of that particular bank and how cash was transferred between banks, or how they could modify account balances, or a large portion of this was actually just specifically controlling ATMs to spit out cash. So they learned that whole system and then started manipulating the system to push cash and transfer money out of the banks. And so this happened at over 100 organizations, and the amount of losses was on the order of $1 billion. And so this is the kind of activity that we need to be able to catch, because that initial access piece, is something that there are always going to be new and better ways of doing that'll get around the tools on the outside. And so a big gap is being able to see, detect, and understand this behavior internally. Another pretty famous instance of this is at the DNC. And so what happened there is that hackers similarly gained internal access, and they were able to maintain that presence inside the network. And they didn't use any malicious tools to do this, right? They were using common kind of system administration and Windows tools that didn't trigger any alerts for the typical types of instrumentation that organizations have in place. And there were even two different groups that obtained access and were able to do this. And the level of access that they obtained, similar to the previous example I just gave, was that so thorough that they were able to watch and read all the email and chat traffic, and so they had a extreme amount of visibility into what was happening in the organization and pulling all that information out. Okay, so it's pretty clear, and we see it in the news every day, and there are unfortunately hundreds of other examples of how this kind of thing is happening, and Yahoo and Equifax most recently. So what I want to talk about for the rest of the conversation today is how we can use machine learning to improve the defenses of companies. And so I'll start that by stating in the negative and how it's not ways that it's not effective to use machine learning for cybersecurity. And there's a lot of hype today about how machine learning and AI can be used in this field, but a lot of it is actually exacerbating the problem. And so one way to do that is by increasing the noise. And so a lot of the approaches that are used today, detect anomalies, and it's on these kind of enterprise networks that are very complex with all kinds of behaviors going on. It's very simple to generate statistical anomalies that are unusual from a probability perspective, but those are not aligned to real risks in the network, right? And so those can be misconfigurations, they can be errors and broken hardware, and they can be non-malicious but unusual behaviors. And so it can really increase the problem for the teams working to defend networks by just throwing more statistics at the problem and generating more alerts, and that's exactly the opposite of what's necessary. Similarly, static understanding of the situation with models that are the same across environments and time. And so, historically, the kind of machine learning that has been used is something that generalizes from the signatures and rule-based approaches that are traditionally used and give you a slightly better ability to detect, but again, on kind of all the old approaches and still focused very much on access and how people get into a network. But it's still around this framework of what was the malicious activity that occurred, or even on the internal portion of this, some of the approaches are looking for this lateral movement of how do I detect maliciously moving between machines. But this kind of static approach is a model that's learned offsite and deployed out to all places to find these kinds of things. But that staticness is exactly allows the adversarial side of this to understand, profile that tool, and then just avoid whatever detections have been put in place. So if the models aren't changing and learning and updating for the environment and quickly adjusting to what adversaries might do, then that's another deficiency of a lot of what today's approaches are. And then finally, these black box results are models and approaches that don't explain why an alert or anomaly is generated. And so that limits the ability of security analysts that aren't experts in machine learning to take these results and act on them, or build trust in them, or understand why it happened, and potentially how to provide feedback to improve it over time. And so this kind of opaqueness that can occur when you just throw an algorithm at a problem and don't present it to the user in a way that they're able to understand it can severely limit the applicability and actionability of what's how it's able to be used. All right, so in contrast, the way that we're going about this, and that I think the way that the whole industry is moving is there's a need, first of all, to focus on the objectives of what an adversary is doing. And so this makes it much more difficult to avoid detection when the modeling is focused in on the area of behavior that is difficult to avoid. And so to achieve the objectives once you get in, there are some things that are very difficult to avoid. The particular tools and binaries and all the kind of things that are caught with signatures are easy to change and modified, right? So that you can miss detection. But the need to move between machines and find the data and move the data and eventually move the data off the network is much more core to this. And so it, machine learning approaches that focus on those core behaviors are critical. And then an adaptive understanding that learn in particular environments, because what's unusual in one environment is very different than another. Large companies' networks vary significantly, and so the ability to understand what's normal on a particular network is critical here, because the whole point is to kind of distill all this information down into a framework that a security team can act on it. And so if it's not understanding the particular environment that they live in, then it further wastes their time. And so the ability to really have the model adapt to the environment that it lives in, and also over time as that changes, is really important, because a lot of static approaches will not be able to understand the very simple things that happen on a network, like an infrastructure server that backs up once a month. That can look like a large data movement that might be malicious if you weren't able to learn that that's the kind of behavior that happens normally on this network and understand what machine and what resources do that. And so the ability to come into a particular network and learn that information is important. And then finally, this ability to generate interpretable and actionable results is, that the models are able to explain why they're, how they learn the network and what factors are leading to that prediction, such that it can build trust with the analyst and also provide the kind of diagnostic depth that allows feedback to be given and improve that over time. So a little bit more detail on each of these pieces. So it talked about how the need to focus in on these core behaviors allows us to reduce the false positives by not looking at hundreds of different behaviors that may or may not be related to what the actual goal of an adversary is, but drilling into the specific ones. And so just to give a little more detail there, in the reconnaissance phase, that looks like talking to too many machines relative to the expected role of that particular machine or user on the network. And similarly, the successive communication is over too many ports, and to what kind of services is it interacting with. In the collection phase, that's about how much data is being moved, so the volume of bytes being moved, and the kind of directionality and consumption ratio, like is this particular connection pushing data or pulling data in the overall ratio, and how many things are involved. And so a person in their typical role may interact with this, normally a single database and probably even just a portion of that database. If someone's suddenly pulling from all the databases in the enterprise, or at a depth and breadth within a single data source that's unusual, that's an important behavior to be able to detect as well. And then finally, on the exfiltration side, once all of that previous activity has happened, then it's about understanding the outgoing byte, publication type of behaviors, and how rare is the external destination that it's being communicated with. A typical behavior for a lot of these sophisticated adversaries is to have, be able to push the data to an endpoint that's unknown, doesn't look like it's malicious, but it's oftentimes, only the compromised machines on the network will be communicating with that. And so that's one of the important things to be able to understand is that particular external resource something that's just being communicated to by this particular malicious actor inside a network. There's also interesting need to be able to look for intermediaries, and so also possible to publish it to other shared and public type of places that you can use cloud resources and cloud vendors to push data to, and that requires another different type of ability to find data going to those type of external resources. So to do all this in the kind of adaptive way that I was talking about, it's important to be able to learn on the data in an environment. And so this is, Adversive, what we think about as the framework for being able to do that. And so the kind of underlying all of this, we work on top of the Hadoop framework. And so that, for a lot of companies, and especially some of the largest companies where this is of high importance to them, their data, it's important to them that the data, and even at the magnitude of data as well, can be complicated to get it outside the network. And so the ability to run this on top of resources within their firewall and on their inside their data centers and not have to push it all up to the cloud is an important aspect. And then being able to prepare that data means taking the raw logs and extracting it and understanding the behaviors that exist in those logs. And then we have an automated iterative modeling process that tries a bunch of different modeling approaches, and that incorporates both the feature engineering aspect as well as the parameters of the particular models, and then finally generate results that can be consumed by those analysts. And across the top is this methodology for presenting them in a way that's interpretable and actionable and allows them to give feedback and be able to look at them, understand them, say when they're working, when they're not, and have a level of detail about why the model presented a particular result that allows feedback to be injected back into the more automated process that we have that's on an ongoing basis, taking in new data, learning the new normal on that network, and generating results that are most valuable. And so just one more level of detail about what that looks like is there's many different data sources that contribute and give visibility into these different types of activities. So proxy logs are the data that sends or that tracks web-like behavior for the most part from internal resources out to the internet. NetFlow gives us the most detailed understanding of how machines both internally and from internal to external are communicating across the network. And then DNS and auth and DHCP logs are other types of data sources that give us additional context. And so from this, we want to detect anomalies about, related to the behaviors that I've described earlier in the talk, and then put these in context across this kind of adversary lifecycle so that a security analyst can understand this, assess the risk, and act on it. And so the kind of case that we're able to construct when building these individual models and tying it together across time is like what you see on the right here, where we're saying that a large number of servers have been contacted by this particular host, and we saw that a lot of data was moved internally and then finally started to get pushed off externally. So we're saying, 300 internal hosts were talked to by this machine, but only 3 were typical or would have been expected based on the models that we learned about this network and this particular machine. And then 2 terabytes of data were transferred internally to this machine, where 50 megabytes was what the models had learned. And then finally, that 5 gigs got pushed from this machine off the network to an external resource, where 35 megabytes was the kind of learned and expected amount of data that would have been reasonable for this machine to interact with that type of external site. And so it's important, and a lot of the development of this product with our customers has been about how to take the underlying machine learning models, distill them down to what's expected on a network, and then present it in this framework that allows them to understand it in the context of how they are responsible for securing and defending the network. And so this helps assess the risk. The most security teams today have to deal with a bunch of different tools and disparate sources of data and alerts that only look at one particular part of what an adversary might be doing on the network. And so it's a manual job, and sifting through hundreds or thousands typically of different alerts and trying to piece this all together themselves. Whereas when we take a more holistic approach, understand all these behaviors and pull them together into this overarching framework, it makes it much more actionable, and also reduces the false positives by being able to look through all these individual pieces. So give you a little bit more detail now about how we're using machine learning for detecting cyber adversaries. So like the first step is looking at these primary internal behaviors, and then applying machine learning across individual behaviors of each of these, across the multiple data sources, and then putting it together into a framework that allows you to assess this. And I'll go into a couple of examples at the end here of how that looks when you pull it all together. The kind of pipeline for how that happens is these raw sources ingested, extracting the behaviors, modeling them, and then building the cases. And so this all sits, like I mentioned, on top of that open source software. We have our own Spark libraries that extract these behaviors that are material and build those models in a scalable way, and then present those out via API or in our web UI. And so, doing this on Spark allows it to scale. We have to be able to ingest up to petabytes of log data for working with the security sources that, on large networks, it can scale to that as you look at months and years worth of historical data. And so Spark gives us that flexible and efficient platform for transforming all these sources, and also allows us to do scalable model learning across a cluster of machines. And the next step is this learning of normal, where we model normal for individual behaviors. And so our approach to that is to start simple with linear models. In this allows us to get robust, explainable models to start with. And layering in the attributes of the entities on the network helps to understand normal in context of what we know about the machine. And we can also incorporate analyst feedback about a machine or a particular set of entities on the network. And then we're also looking at deep learning for learning implicit context and understanding that more richly, but there are trade-offs there as well, because that can limit the, this ability to explain what relationships are discovered. And so that's something that we're actively exploring there. We find that the linear models, at scale with a lot of data, give us sufficient results to get quality that solves this problem in a way that customers haven't been able to see previously, but certainly an active area there that we're pursuing. And then finally, from these individual models, we're linking across behaviors to present it in context and connect across multiple entities is something that I'll talk about at the end. So here's an anonymized customer case study to give you a kind of tangible sense of what this looks like in the real world at a large customer. And so we have 5 data sources that come into the system. And so that's the proxy logs and the DNS logs, router logs, database logs, and endpoint logs. We're looking back over 60 days for the analysis period here, and there's over 150,000 hosts on this network. kind of behaviors that observed over this about a month of the modeling period was 3 terabytes of data moved internally, 5 gigabytes that were transferred off the network to rare external domains where only one host had talked to that domain on the entire network over that entire time period. And that was out of a total of 12 terabytes that left the network over this time. So when we break that down into, what's the prevalence of these behaviors inside of a network, and that our models have to be able to learn and understand what's normal and how to distinguish unusual behavior. So at the top line in each of these 3 columns here is kind of how many hosts had some amount of material behaviors. And so in reconnaissance, over 70,000 hosts were doing some amount of internal DNS lookups. 9,000 hosts were moving data internally, and 60,000 hosts had interactions with where there was external internet interactions. And these are kind of descriptive statistics as our model scores increase in anomalies. So these aren't rules from the model, but kind of descriptives at different percentiles in the model score. And so the next level down here, there's still 30,000 hosts that looked at 5 other internal destinations. 3,000 hosts that consumed material amounts of data, and 8,000 hosts that talked to rare domain. And then finally, even as we get to quite elevated scores in an individual stage, there are still 3,000 hosts that did over 500 reverse DNS lookups, more than 300 hosts that consumed over 100 megabytes of data, and over 100 hosts that published more than a megabyte to a rare external domain. And so when you're looking at individual behaviors, even aligned to the adversary objectives, they're still generating hundreds or thousands of alerts. And so that's the kind of current state of the art in the industry, is that you're stuck trying to wade through all these, set up heuristics, and understand how to do this and assess the risk. But in our approach, we connect across all of these. And so there's only one host that lit up this entire life cycle at an anomalous level. And so that allows us to distill down to a very small number of cases that really need to be investigated. So one of the difficulties in this problem is that there are very few public data sets to really validate the accuracy and validity of an approach and models. And so the one that exists out there comes from Los Alamos National Labs. You can look this up online and find it. And so they have basically about a month of data where they captured internally, and they also had a red team, which is this kind of, you explicitly sanction someone to do malicious activity on the network so that you can observe and track and then use it for testing. And so there's about 1.6 billion events in this data, and it has NetFlow DNS authorization and process logs, as well as labels of the malicious access that occurred during this time period. And so this is an example of what that data looks like in our system. And so the top case here was the main red team host that we find with our machine learning. And so I'll drill down, and we break this down into the recon collection and exfil. In this particular data set, it doesn't have that external interaction. And so there's no kind of public data source that has the full life cycle of an adversary. So it's something that could definitely help the field if we can make this kind of available more broadly, or generate some data sets that have this full life cycle. But for now, this is the best we have. To give you one more level of detail here around the kind of individual behaviors that triggered that generated high scores in our system. So you see, something like pinging 14 distinct IPs with SNMP on the network generated a very high score, because would have expected less than 1. So almost that was very unusual given the context of what the models had learned for this host. And then the next one down here is that over 300 distinct IP port pairs were contacted with ports that relate to data services, and 6 would have been what was normal given what we had learned from historical data. And so on down the list, these are the kind of events that can, in accumulated together, this makes it pretty clear to a security analyst what's going on and the egregiousness of what's happening. The last piece here that I'll end with is the next level of difficulty is multi-host adversary behavior. And so this is where there's the advanced adversaries tend to compromise multiple hosts on the network. And so understanding how they're connected is the other aspect of this problem. And so you might see the reconnaissance happening in a particular machine, and then the data captured and collected on another, and then finally moved to a different machine to exfil it off of the network. And so it increases that problem of how you can pull this all together and present it in a way that allows those all to be connected while maintaining a low false positive rate. And so that's one of the pieces that we also provide in our product, but is an ongoing problem. So just to kind of finalize, in terms of how machine learning applies to all of this, it's an anomaly detection framework, as has been obvious, I hope, in the presentation here, because there's no labeled data available for what these adversaries look like, and it's a adversarial problem where it's constantly changing, and so just learning a historical approach is not going to be sufficient. And so the overall prospect for the field is how we can understand normal in a network and successfully identify these anomalous behaviors, connect them together while maintaining a low false positive rate that keeps it in line with the business risk. So, not all anomalies, but just those anomalies that line up against how adversaries are trying to act on the network. So that's there's lots of interesting work to continue here, and lots to be done. We're definitely hiring at Versive, and would love to hear from any of you that would like to come join us in solving this problem. For the next year, this is our primary focus, but we think we have a good handle on this and are starting to show the value. And over time, we'll also be releasing additional products on our core platform that solve further use cases that these large companies have for machine learning. So I'll wrap up there a little bit early, but give some time for questions. So are the ML algorithms we're using open source proprietary? We have built our own internal, basically gradient descent algorithms, and so they're similar to what you would find in MLlib on Spark. Although, the automation that we've added on top of that around feature engineering is proprietary. That is, because we've found that it's very scalable, fast, and efficient to use linear models, but they have deficiencies, obviously, for capturing the types of nonlinear interactions that are required to get state-of-the-art results. That piece is part of our proprietary technology, and doing that efficiently and at speed and at scale. But it is, in terms of how we work with customers, we sit on top of that open source Hadoop and Spark stack, and so that's what the mix is for our technology. Really appreciate you guys all coming and listening. What are some examples of tools inside the open source stack? And so the HDFS is the distributed storage that's important for storing the large scale data that customers have. And on top of that, Spark is the primary tool that we're using. It's very flexible, MapReduce in memory, and so it's efficient and scalable. So those are the primary pieces that we use. There are definitely other aspects of the Hadoop stack. Kafka is something that's used by other pieces of the kind of security ecosystem to pull the log data in from the producers of that data and get it onto Kafka. K-A-F-K-A is a kind of queuing and streaming data infrastructure for pulling that data from producers, from log producers, and coordinating that. Onto HDFS. And so that's just kind of the mechanics of getting the data in there. And then Marnie asked about prevention versus detection, and any thoughts on predicting rogue behavior that precede attacks. Yeah, so it's definitely, the earlier you can find this behavior, the better. And so, we look to identify it during that collection and reconnaissance, those earlier portions of the internal activity. So hopefully it can detect something with high confidence at that phase. And even during those phases, there's typically still a little bit of external coordination or command and control with the outside world. And so that our overall approach is to kind of see the early stages of that adversary life cycle to allow a team to stop it before there's a large loss of data or information. Doing that even earlier from the outside is that kind of adversarial game of, the most sophisticated adversaries understand the types of ways that are that people look for that from the outside, and so they're constantly trying to stop and profile in different ways from the outside, and so it's difficult to catch all of those. And so our assumption is that the most sophisticated and well-resourced and motivated adversaries will find a way to get into a network, and that the part that is most difficult for them to change is how they move inside the network and move data and get data out of the network. So how long does an adversarial event typically take? So there's a spectrum there. So some things people call them like a smash and grab, where you come in and grab something and the whole thing might only last a day or two. But the typical lifespan or the detection time of these more sophisticated attacks is, depending on what kind of survey you look at, can be over 200 days. And so some of the recent examples like Equifax, they had access for months, and they were kind of slowly siphoning off the data. At Yahoo, quite a long time period there as well. And so it all kind of depends a bit on the particular attack and what the goals and motivations are. The most sophisticated attackers want to basically maintain presence as long as possible, and so they try to behave in a way that avoids detection and maintains that persistent presence, because there's kind of ongoing value to being able to capture the most recent data, and so being able to stay with persistent access indefinitely would be a goal in a lot of situations. The shorter ones are those where there's maybe just a specific piece of data, or in a more organized crime-driven scenario where they're looking for just a particular short win in terms of financial gain or data that they can sell, then those can be faster timelines. Yeah, the Carbonac one, that was happening over months, and so it varied by organization there. But they infected a long list of organizations there, and just kind of kept acting at each of them until they were detected. And so that was a ongoing behavior. Well, great. I think that wraps up the time slot that we had. So very much appreciate all of your time and coming to the talk, and enjoy the rest of the conference. Thank you.